Today I'll be proving that if you have a set G of all 2 times 2 matrices whose entries are rational numbers and whose determinant is of the form 2 to the power of n for some integer n, we'll prove that G is a group with respect to matrix multiplication. Okay, so you got 2 times 2 matrices. All right. So the first thing we'd want to prove is that this set is closed with respect to matrix multiplication. So we'll first prove that if you multiply 2 of the matrices, you still get the matrix you get as a result is still in the set. So what we can do is we can let A equals the matrix A, B, C, D, and this has rational entries. So A, B, C, D are rational, so are in Q. And also determinant of A is equal to AD minus BC. And let's say this is of the form 2 to the power of x, where x is an integer. So it could be positive, negative, or 0, the value of x. And similarly, we can let B is equal to, the matrix B is equal to E, F, G, H, where again, E, F, G, H are rational. And the determinant of B is equal to E, H minus F, G, and is of the form 2 to the power of y. Okay, so now we have this. Now what happens if we multiply AB? So this is going to be our operation involving our set of matrices. Now we have ABCD times EFGH, and this equals AE plus BG. So doing matrix multiplication, AF plus BH, CE plus DG, and CF plus DH. And now important note is we want to prove all the entries of the matrix AB are rational. And this is true because whenever you multiply or add rational numbers, whenever you add rational numbers or add or multiply rational numbers together, the result is always rational. So in this case, we have all the numbers, all the letters A, B, C, D, E, F, G, H are all rational. So any combination of adding and multiplying them will be rational, which means all these 4 numbers, AE plus BG, AF plus BH, and so on, all 4 of these numbers are rational. So this means the first test for matrix AB being in the set is passed. So all 4 entries are rational. Now we'll have a look at the determinant of matrix AB. This will equal this times this minus this times this, which is equal to AE plus BG, CF plus DH minus AF plus BH, AF plus BH, and CE plus DG. And this is equal to, from expanding, AECF plus AEDH plus BGCF plus BGDH minus AFCE minus AFDG minus BHCE minus BHDG. Now we have some cancellation. So the BDGH cancels out and the AECF cancels out. So we're left with AEDH plus BGCF minus AFDG minus BHCE. And this can be factorized as, okay. Oh wait, this should say AFDG. Okay, Now we can have a look at these two terms, and we see there's a common factor of EH. That's AD minus BC. And we can also do the same thing here. So we have a common factor of FG. And this is BC minus AD. This can be written as AD minus BC and EH minus FG. Okay, and this, in fact, this is equal to determinant of A times determinant of B. And this means determinant is 2 to the x times 2 to the y, 2 to the x plus y. And x plus y is an integer since x and y are integers. So determinant of AB is of the form. So the determinant of AB is of the form 2 to the n, where n is an integer. So it means you've successfully proven if A and B are in the set G, then AB, all entries are rational, and determinant is of the form 2 to the power of n, which means if A and B are in G, and the product of A and B are in G, okay, so then you can say it's closed under the group, just closed under the operation, operational matrix multiplication. Okay, now we need to show the existence of an identity element to prove it's a group as well. So the simplest possible option for an identity element will just be the identity matrix. So this is to check it's part of the group, or check it's part of the set G. You see, it clearly has rational entries, and the determinant is just equal to 1 times 1 minus 0 times 0 equals 1. And this is also a power of 2. So I is in the set. And this satisfies AI equals IA is equal to A for all A in G. So by the definition, by the property of the identity matrix, AI equals IA equals A. And this is enough to show the existence of an identity element. So I is an identity element. The final thing to show is the existence of an inverse. So existence of an inverse element for all matrices A in the set. So again, I'll rewrite the matrix A as this, which is in G, and again, A, B, C, D rational, and determinant of A is equal to AD minus BC is equal to 2 to the x. Okay, and importantly, determinant of A is not equal to 0, which means there exists an inverse matrix for A, because the determinant is an integer power of 2, which is not equal to 0. So the inverse is equal to the inverse of a 2 by 2 matrix is 1 over AD minus BC, and we have DA negative B negative C over here. So that's going to be our inverse matrix. And our determinant of this inverse matrix is equal to, we have the factor of 1 over AD minus BC out here, and times AD over here, and minus negative B negative C. This is equal to 1 over AD minus BC. Okay. Oh wait, this should be squared. Okay, because when we take this factor into here, we'll have to multiply it by itself when we're doing when we, for example, we have d over AD minus BC and negative b over AD minus BC, negative c over AD minus BC, and a over AD minus BC. That's why the AD minus BC is going to be squared. So we have 1 over AD minus BC squared times AD minus BC, and this is equal to 1 over AD minus BC. So AD minus BC was 2 to the x, so we're going to have 2 to the negative x here. So negative x is still an integer, so determinant satisfies the condition for being in the set G. And again, since A, B, C, D are rational, so now we have division involved. So again, any combination of adding, multiplying, or dividing rational numbers is rational. And also, the denominator of these fractions is not equal to 0 because AD minus BC is equal to 2 to the power of x, which is not 0, which means all entries of the inverse matrix are rational. And this means the inverse matrix is in the set G by combining the two facts. Now, by using the matrix multiplication operation, we have A inverse equals A inverse A is equal to the identity element I for all A in G. So this shows every element of G has an inverse. So every element in G has an inverse within G. Okay, so this means all the group axioms are satisfied. So the group axioms, you have associativity, existence of identity, and oh wait, hang on, we haven't proven associativity, so I almost forgot that. So for associativity, we have for A, B, C in the group, since matrix multiplication, wait, A, B, C, since matrix multiplication is associative, so for all A, B, C, and G, matrix multiplication associative, which means this operation is associative. So this proves associativity. And now finally, all the group axioms are satisfied. So it means the set G with respect to matrix multiplication and this is a group. Okay, so successfully proven that all 2 times 2 matrices with rational entries and determinant of the form 2 to the power of n, this forms a group with respect to matrix multiplication. Okay, so that's all I have for this video. Thanks for watching, and I'll see you next time.